Okay, so this is the fall 2018 midterm 2, question number 7, Trictionary or treat. And let's take a look at it together. We're just going to walk through the question, try to figure out how you would approach it, and why the solution is what it is. So it's fairly common that there's some new definition of something that doesn't really exist in the world, but it's just made up for the exam problem. And that's true here. So a Trictionary is a pair of tree instances, K and V, that have identical structure. Each node in K has a corresponding node V. The labels in K are called keys. Each key may be the label of multiple nodes in K. What does that mean? Well, it means the same number might show up twice in the K tree. And the values for the key are the labels of all the corresponding nodes in V. Okay, so there's like a corresponding node here and here. So 7 and C correspond is, I think, what it means by corresponding nodes. We'll find out. A lookup function returns one of the values for a key. Specifically, a lookup function for a node in K is a function that takes V as an argument and returns the label for the corresponding node in V. Okay, so there's a function for each place, like a node is a position. There's a function for each position where if you pass in this whole tree, it returns just that label. Implement the function lookups, which takes a tree K and a key. It yields all lookup functions for the nodes in K that have key as their label. The new lookup function is part of the implementation. Okay, so here's an example K tree, an example V tree. Oh, and here's the correspondence. So like there's two 2s and they correspond to C and A, which is where the values are what they are. And here's code to define them. So, before I look at well, I wrote this problem, so I can't really tell you how I would solve it from scratch. I will pretend to simulate that to the best of my ability. The way I thought about this was, if there's a function for every position that's supposed to take in this tree and give you the corresponding label at that same position, how is it going to get there? It feels to me like the function corresponding to this position is going to get this 6 by taking in all of V, looking at the branch at index 1, looking at the branch at index 1, and then the label there. So if there's a function for each position here, then that means there's kind of like a path through V that's going to get you to the corresponding position in another tree. So as I'm thinking about how I'll make progress, it has something to do with describing for where you are in K, what's the path through V that's going to get you to the same spot. And it turns out that the path through V is the same as the path through K. So like to get here, you also do the first branch at index 1, branch at index 1, look at the label, and that's how you get the 4. Same process gets you the 6, just for a different tree. So how did I get here? I mean, like I read all this block of text, which this is on the long end, right? And I really keyed into there's a lookup function. Oh, here. A lookup function for a node in K is a function that takes V as an argument and returns the label of the corresponding node in V. I think the risk of reading a sentence like that is it just sounds like nonsense. And the way to have it sound like something useful is to focus on a specific example. So a lookup function for a node in K, let's just pick a node and then say, okay, what would the lookup function do? It takes in all of V and gives me back A. How's it going to get A from all of V? It's going to look at the branch at index 1's label. So I find problems like these, which basically all problems that have some definition of a structure, to be more useful if you look at a specific example of that structure. So now we have to write some code. There's 2 parts here. Yield a lookup function for each node of K that has the label key. Well, I think whenever you're trying to do something for every node that has a particular label, then you're going to end up traversing the whole tree. And when you find a label that equals the key you're looking for, then you're going to yield something, is what it says. So K is a tree. How do we know that? Well, the example we got is a tree. And that's exactly what seems to be used in the doc tests. And so, things you can do with a tree are look at its label, look at its branches. That's kind of it. Or ask if it's a leaf. But this seems like more of a check the label kind of scenario. So yeah, like if k.label equals the key that we're looking for, then maybe we've done something useful. Okay, so then we need to yield the lookup function. And we don't really know how to do that yet, except for there's this new lookup. So it probably has something to do with that, but let's just delay it for a while. So we're somehow going to build a lookup function. Otherwise, we go through for I in range len k.branches. Okay, so we'll go through all the branches, but instead of looking them up just like the branch itself, we're also keeping track of the index. And it appears that that's important because when you call new lookup, you have to pass in the index of a branch. Okay, so yeah, I would probably make a little note to myself here. It says I is the index of a branch. I feel like we're making progress. So if we're trying to traverse the whole tree, then we want to call lookups on each branch. So we're going to have some k.branches I. And as with almost all, well, basically any way you want to traverse a tree just means like call lookups on the root and then call it on each of the branches. That's how you traverse a tree. So we're going to call lookups on this thing and key. So I haven't really done much work in terms of solving this problem. All I've done is fill in the stuff that kind of makes sense. Now is the moment where we have to actually figure out how we're going to build these lookup functions that we're after. But I think we have some useful clues. We know that when we find a node that has the right key as its label, it's time to build a lookup function. And pretty soon we're going to describe what that is. We also know that we're going to go through all the branches by their index, and we're going to call lookups, and we know what lookups returns. Lookups returns a generator, which is an iterator, over all of the ways in which you'd look up, that you'd build these lookup functions if there wasn't all of K, but there was just one branch within it. So those are the two pieces of the problem we still have to solve. And this is just a note that we left here. So I think the base case is a little bit more approachable. What do you do if you find the key right at the root of the tree? So we looked in all of K and we found 5 right at the top. And now we're supposed to return a function that if we passed in V, we would get go. Well, here's a function where when you pass in V, how do you get the root label? I think that is just v.label. So we've kind of like handled the case in which the key that we're looking for is right at the top. What we haven't done is handled the case where what happens in a recursive call. So in a recursive call, we found the 5 at the top. That's easy to handle. Sometimes we find the 5 in branch number 2. In that recursive call, we're going to return a function that just looks up the label. But to find the L, we don't want to just find the label of all of V. We want to follow the right branch, the branch at index number 2, and then find its label. So when we make this recursive call, pretending that K is 5, we're getting back a function that looks up the label of whatever we call it on. And we want to like build a larger function, something that will not just look at the label, but it will look at the branch at index 2 first, and then get the label there. So I think we need a name for this function that gets the label. And since there might be more than one such function, we can give each of them the name lookup. And I guess we need a colon over here. What I'm thinking now is if originally, should really get a tablet. If key was 5 in the first place, then now, and lookup is just lambda v dot label. Shouldn't these have like a nicer color? How about magenta? I like it. And what we need to build is a function that will get me L when given V. So that should look something like lambda V gets branches 2 and then the label. So all I'm indicating here is that it's very helpful to think about an example. Why did I pick 5 as the example? Well, because it was at the top and I wanted to kind of check my base case. And then why did I pick it again? Well, because it's also here just a one level down. So it's kind of easy to reason about. You're going to hit the base case after your first recursive call in here when I is equal to 2. What you're going to get back from your recursive call is just lambda v dot label. And my goal would be to yield this longer thing. Take in v, get branch at index 2, and then get its label. And somehow, new lookup needs to do that. Yeah, okay, so now we have a call to new lookup where we actually know what the arguments are. So in that case, this is 2. This is back when we originally passed in 5, and we yielded the one for the root, but now we're working on this one down here.
Okay.
We know that I is 2 because that's what branch it's in. And we know that the lookup function that we got from our recursive call is just lambda v dot label. And we know that what we're trying to build is this. Okay, so now to build a new lookup where we have a position, which is like which branch you're in, and we have an f, which once you're in the branch, it knows what to do with it. How do you write a new function that handles the whole tree? So basically, we're trying to get to this from these two components. We could try to put them together as follows. Oh, I think we're not supposed to be magenta anymore. We're supposed to be black again. A function of v that looks into branches I. And then what do we do with this? This is another tree. And we want to get its label. Now, there's like some ambiguity here with this example. Like maybe we just do dot label. But we have a lookup function f, which gets its label. So a more generic version is to call f on that, which in the case that I was 2 and f got the label would give you start with v, get branches 2, and then get its label. The more general version of what's going on here is f knows how to look up a value in a branch. I knows what branch you're in. How do you look up a label in a whole tree? Go into the ith branch and then look up the label within that branch. How do we know what the different values or different functions we're passing into new lookup are? Well, let's look at where they came from. They all came because they were yielded from a call to lookups. Therefore, they either come here, so some of them look like that, or they come from here. So some of them look like that. So that means all of the lookup functions we'll ever see are either just look up the label or go into a branch and then do some lookup. Okay, now we've hit something kind of recursive. There's two possibilities. This f is a lookup function. So f could either just look at the label or go into one of the branches and then do a different f, which could either be just look at the label or go into one of the branches and do another lookup. So I guess like the general space of all things that a lookup function could be is it could go into some branch and then go into some other branch, and then go into some other branch and do that for a while. But eventually it's going to have to look at a label because that's kind of the first thing that you ever build a lookup function out of. Oh, great question. So why are there yields here instead of returns? Lookups on the number 2 for this example gives you back two different functions, one for this node and one for this node. When you call those functions, you get C and A, which is why we finally see this here. So when you're looking up a 2 in this whole tree, you might find it more than once. And what's the whole point of yield? Well, yield, like its important property is that you can yield more than once. Whereas with a return, you have to like build up the whole return value and you can't return until you find the whole thing. With yield, if you find just one piece of the answer, you yield that. And you go through and you do some more work until you yield all the pieces of the answer, and then you're done. So the way lookups is structured is to yield a lookup function every time you find one that matches the key. It happens to be that there are 2 in this call. Happens to be there's only 1 in this call, and there happens to be none in this call. But these 2 correspond to 2 different yields. If you had returns here, this returned a function, this returned a function, then when you called lookups, you'd only ever get one function. And that function could find either C or A, but it couldn't find both. So the point of having a yield is that we call lookups once, we get all the different things that match the key, and we can go through all of them and get the corresponding values. So, this is the kind of question that basically nobody got right. So if you're studying and you're like, oh, this is making me panic, don't worry so much. People do great in the course without ever solving, question 7 of homework of fall 18. But at the same time, I do think it's instructive because it tells you about one of the many things that a function can do. In this case, a function is representing a path through the tree. And the way you build up that path is you kind of start with a function that just looks up a label and then build longer functions that first look up a branch and then look up the label, or then look up a branch and then look up a branch of that and then look up the label, etc. And so it's combining, a lot of different ideas from the course. Instead of a dictionary being built in, now it's built out of trees, and you have to know how trees work. And how do trees work? Well, they have paths. And if you want to replicate a path through here with a path through here, you could do it with a function that basically just does the same operations. Go into this branch, go into this branch, look up the label. It's exactly the same way that you would find the 4 here or the 6 here. Great. So we're in fall 2018 midterm 2 question 1. And we're going to do the first 3, and then who knows, maybe we'll do more than that. So there was a suggestion of draw an environment diagram. Sounds reasonable. I'm going to draw kind of a sketch of an environment diagram, and we'll see how detailed it gets. But you do have to execute the class statement, execute the class statement, execute this line and this line before you can ever really make any progress on these. So let's go through and talk about exactly what happens with each of those. So we're going to build class A. When you execute a class statement, then you do go through and set its class attributes. So I'm just going to draw the class like a frame because they kind of behave in the same way, not identically, but pretty close. And let's make this 3. we've got another class, B, with its own class attribute, X, which is a list. I get a little scrunched here, but I think it'll work out. This is probably the worst drawing tool I've ever seen. Okay. Which has a 5 and a 6 in it. And then we make a B instance. Oh, this is interesting. So when you make a B instance, then you execute the init function for the B class. So an instance is also kind of like a frame. So here's a B instance called B. And what does it do? It gets passed in as self along with Y, where Y is a list containing 1 and 2. And self.a is assigned to x1, which in that case would be the number 2. So you have an A, which is the number 2. Then this says Y. We have to look up what Y is. Oh, Y is this list, and it gets changed to 8. So I never drew this list anywhere, but we certainly have to draw it because we're about to change it. So the list 1, 2 that we were editing now has new contents. It has, originally it was 1 and 2, and now it's 1, and we assigned Y1 to 8, so now we have an 8 in here. So this is X in the global frame. So label it there. Here's our A class, here's our B class, here's our B instance. And now we have to make an A instance. So when you create an A instance, you have to execute the init method for the A class, which creates a self.a bound to the number 6, which is what we passed in. It creates a self.x bound to B. And what is B? Well, that's B from the global frame, which is this B instance. So that. And it's got a special self.stir, which is something that I guess we won't get to until we go back and do it. But let's just ignore that for now. Okay, now I think we can finally do some work. So what happens if we go through A and B and get the attribute.a for each one? Well, for A, we're going to get 6, and for B, we're going to get 2. We're going to put those together in a list, and we're going to get the list 6, 2. So what would happen if we looked up A.x? Well, we get this B instance, and we're going to print it out, which means that we have to invoke the stir method for the B instance. We look in the B class, there's no stir method. So we look in its base class and we find the stir method, which returns BB. So that is what it looks like when you print A.x. What does it look like when you print B.x? Well, B has no X attributes, so we look in its class. Its class does have an X, which is a list containing 5 and 6. And when you print out a list containing 5 and 6, it looks like that. Now we're going to print out B.y. Here's B. It has no Y. So we look in its class. It has no Y. So we look in its base class. There's a Y. It's the number 4. Now we're going to print out X. X is this list containing 1 and 8. Yeah, great question. So the question is, how come the B instance here doesn't have a Y attribute? Even though within the init, Y is mentioned and changed.
Yes.
This is like a fact about how Python works, is that a Python instance starts out with no instance attributes. They're only added whenever you use a dot expression on the left-hand side of an equals to add an attribute to that instance. For init, that instance is called self. So if you want to give attributes to the B instance, you need to write self dot, and then the attribute name, and then an expression that gives you its value. Other expressions that don't involve self dot something equals will be executed. They just won't change the attributes of self because self isn't mentioned here anywhere. So I would say that the code within the init method isn't really special at all. It runs like any other code that's elsewhere. Might be in some other method, might be at the top level, might be in the body of some random function somewhere. There's like nothing really special about the way these things are executed. So for example, they don't automatically create instance attributes. All they do is take whatever is y right now, and in this case, change it. And how come we can refer to y at all? Well, y is the name of the argument that we passed in when we created the instance. So what is special about init is that you never see .init with parentheses after it called down here, and yet it gets called anyway. Init's special because every time you make a B, init gets called on that new B instance and some other stuff that you passed in when you created the B. But other than that, it just behaves like an ordinary function. Yeah, good question. So how come you can change y, which is really x out here, even though you're inside of some function that's inside of a class? And again, the answer is that's how Python works. In Python, if you make a list which is mutable, any code that can refer to that list can change that list, even if it's like deep within something else. So if I have a f, which is a function, and within that I have g, which is some other function, and way in here, what am I going to do? I'm going to print a plus b because that sounds nice, but then I'm going to change b. If I call f on some list, get back a g function, and I pass in x, then what's going to happen? A is 789, B is 12. So printing A plus B is going to give me 78912. But this line ran, B was just another name for X, and pop removes the last element. So now X is shorter than it was before. Yeah, that's a great question. If I had an X right here instead of the Y, would that be allowed? And what X would it be? Yes, it's allowed. And it would in fact be this X. Even though there's another X here, this X is part of the class. And the only way to refer to it is by referring to the class or an instance of the class. This X is in the global frame. Basically, any code anywhere can refer to stuff in the global frame anytime it wants. And so, yes, you could write x1 equals 8 here, and it would be changing this X. Just like y1 equals 8 changes that X because y happens to be another name for X. But even if you hadn't passed in X, you'd be able to change it. So the question is, how would you recommend getting started with exam problems that have skeletons given? Because if you solve a problem, it might not be very structured. And, paying attention to the structure is important to getting it entirely correct. Great question. I actually do recommend just kind of trying to solve the problem without worrying too much about the skeleton code that I provide, because usually like how you solve the problem involves recognizing what you need to get done in order to get to the output from the input of the function. And the skeleton code, sometimes it's helpful, sometimes it's just like not that helpful. But if you figure out how to get from the input to the output, then whatever you figured out will almost certainly be relevant to solving the problem. And so a good idea is to read the question, look at an example from the doc test, and ask yourself what process would get me from this input to that output, and jot down things that are going to happen along the way. Like, oh, I know I'm going to have to build a list comprehension that gives you all the integers because I'm trying to pick the biggest one, or whatever it is. So yeah, I think that not looking at the skeleton is an important part of problem solving. At some point, you do have to look at the skeleton in order to answer the question. And what is that point? Well, I think either one of two things happens when you just read the question and look at some examples. Either you have a pretty good idea for how the solution is going to go, at which point your goal is to understand how to fit it into the skeleton. And occasionally people have problems with this, but more often than not, like they find a way to coerce, their idea into the pattern that's provided. And that might require thinking a little bit, that's fine. But usually like every reasonable solution has the same elements in it. Like if you're gonna, traverse a tree, you're always gonna go through all the branches, and that's gonna be somewhere in the middle of the skeleton. The other option is you just don't know what to do, at which point I think the skeleton can give you clues. And this is the part of the exam that's not really like real life, but sometimes it works anyway, which is that you can kind of look at the pattern that's there and ask yourself, well, I'm stuck with this skeleton. How could I possibly use this? And yeah, that can give you ideas. But if you've gotten to that point, like, yeah, I'm not sure I have a good strategy. I think the strategy that's most reliable is figure out how to solve the problem first and then figure out how to fit it into the skeleton. And yeah, what about the details? I think people who get basically the idea right, but they miss a couple points here and there because of some edge case or some detail, are often not going back and trying every doc test example in their head. And I think that is actually quite helpful, is to go through and say like, oh, if I run my function, which I've just written, on this particular doc test example, will it actually result in the right thing? If the answer is yes, then you probably got it right. If the answer is, doesn't actually handle -1 correctly, then you can go back and kind of fiddle with it. So yeah, that last stage of make sure your solution is right, once you've kind of filled in the skeleton, really is just example based. I think it's probably the most effective way of doing it. Okay, so we're looking at fall 2018 midterm 2 part 2. Implement lowest, which takes a list of numbers S and returns a list of only the elements of S with the smallest absolute value. Yeah, so I guess the story here is there might be a tie for smallest absolute value. And that's why we're returning multiple things. This is an interesting puzzle. Okay, so we're making a function, and then we're going to call it on something. Maybe what we're calling it on is this smallest absolute value. And maybe this part is finding all of the elements that have that smallest absolute value. Maybe. So if that were the case, then y, which refers to whatever this whole expression evaluates to, would be the smallest absolute value. And here we'd go through and check every element and see whether its absolute value is in fact equal to this very smallest one. So yeah, I'm getting something like x is what we're iterating over among all the values in S. And for this example, x will go through and be 3 and -2 and 2 and -3, etc. But y will be 2, the smallest absolute value. And for that reason, we'll only get -2s and 2s.
Oh, okay. I think Yeah, I misinterpreted the question and thought that Y would be the list itself. But yeah, that makes sense now.
Yeah, okay. And so then how would we get there? Well, we'd have to use min to get ourselves one of the things that has the smallest absolute value. And then actually take the absolute value of it, then we get the number two. Yeah, that's a great question. So min never mutates the list unless this function is a function that changes stuff. That sounds diabolical. I don't think I've ever seen that on an exam. But in general, no, min is not changing anything. It is calling abs on every element. So now you like somewhere in Python's memory, it has computed the absolute value of everything in S, but like you don't really see that part anywhere, and it doesn't change S. Instead, yeah, it just helps you find an element of S that has the smallest absolute value. But, I mean, the answer is that you never need super. Okay,
Okay.
so let me start at the beginning. The question was, do you ever need to call super, or can you always just kind of refer to the right class? So if we have A and class, and this has some thing, prints two, this has some different F, which prints three. And
Mhm.
what if there's a long chain? B inherits from B, and it has an F. And you really wanted to do, oh, well, let's have it print 4. And then it has a G. And you want to call F, but you don't want it to print 4. You want it to print 3. How do you get that to happen? Well, there's this super notation, which does the trick. If I build myself a C, and I call C.G on it, then I'll get the 3 instead of the 4. It's totally reasonable to write B here. The difference is that you have to pass in self. And then you get the same, oh, sorry, we have to make it first. Then you get the same behavior. Is
And
one
then,
better than the other? I would say like in all modern Python code that I see super here instead. There are some very esoteric cases in which it matters, in particular in the cases of multiple inheritance. But we're never going to see that in this class. So it's fine to do it either way. And in most practical applications, it's fine to do either way. But this is now the kind of convention for how to do it within Python. This function actually didn't used to exist, but now it does. And yeah, so I guess that sort of answers your question. From your perspective, it's totally fine to just say b.f, but now you have to like explicitly pass in the self. But if you want super to do that work for you, then you could. Yeah, good question. So which self are we talking about? It is this thing, C, which when I say C.G, so that and that are the same thing.
okay.
This self here really just refers to what was before the dot in the dot expression that called G.